Well, Mr. Hyper welcomes you back to this episode A of a lesson, which is very, very amazing. We are still looking at solubility products. And this afternoon, we are going to look at the limitations of solubility product or the conditions of solubility product. Now, the first condition is that solubility products are valid for only saturated solutions. We shall be talking about saturated solutions. Then another one, valid only at constant temperature. Okay. So there is no change in temperature. All right. Then another one also is only applied for sparingly soluble salts. So we have STS, saturated solutions, constant temperature, sparingly soluble salts. These are the conditions. Okay, these are the conditions that we base on. Okay, then the factors, this is my point of emphasis this lesson, the factors affecting solubility of sparingly soluble salts. The first one is common ion, addition of a solution with a common ion. We are going to look at the details, of course. We are going to look at the details about common ion effect. Then we have an effect of temperature, and then addition of complexing agent. In case I see any additional information that you need to know about this, I will be adding it. So this lesson's main important issue is the common ion effect. Common ion effect. Common ion effect. Now, the best way to defeat science is to understand the words common. To be common, if I say, hey, this food is very common, it means everywhere that food everywhere, it's common. Ion charged atom, effect, what it causes. So if the ion is common, what does it cause? Of course, the whole thing is about solubility. Does a common ion, or does the introduction of a solution with a common ion increase the solubility, or it decreases the solubility? So we want to see that common ion introduced to a sparingly soluble solution, rather to a sparingly soluble salt or to a saturated solution, what does it cause? Okay, so now I want us to consider a scenario whereby, let me consider a solute in equilibrium. Consider solute in equilibrium. So if we have solute AB, I'm assuming this is a solid. It dissolves, form, or to establish equilibrium with its ions, that is A ions plus B ions. Now, here the sparingly soluble salt has a B. Okay, is a B. Now, if we bring in another solution, if we bring in the same, if we bring in another solution SC, I need you to observe this. If we bring in a solution SC, a saturated solution containing a B, you realize that the concentration of A ions will increase. What you should note is the solution that is added must be soluble must be more soluble than this saturated solution, than the saturated solution containing AB. So it means that AC is more soluble than AB. In that, initially you had AB, which dissolved to form A ions and B ions. But because AC is soluble, it will completely dissociate from A ions and B ions. But you see that A ions are present in this, and at the same time, they are here, implying that the concentration of A ions has increased. When the concentration of A ions or the ions of A goes higher, it means that the equilibrium now will shift to right, rather to left. The equilibrium will shift to left, whereby the A ions being high in concentration will react with B ions to precipitate AB. Get me very clearly. You had AB as you're sparing a soluble salt. It dissolved in water to produce A ions and B ions. Then you introduced SC, meaning you have increased the A. The concentration of ions of A has increased. So what happens is that from this substance which contains a common ion, we pick that common ion, react it with this, and we precipitate back our sparingly soluble salt. It means that since the equilibrium shifts to the left, then the solubility decreases. So we are going to find out that addition of a common ion or addition of a more soluble substance with a common ion to one of the ions of a sparingly soluble salt decreases solubility. In other words, common ion effect. Addition of an ion common to the ones, to one of the ones of the sparingly soluble salt decreases solubility. You should go knowing this. Decreases solubility. So by looking at all this that I've talked about, we can come up with the definition of common ion effect. Common ion effect. Okay, common ion effect. Let's look at the definition. Common ion effect from what we have discussed. When we say common ion effect, let me remind you again, you had AB plus AQ A plus B minus. You have introduced SC. When you introduce SC, it means that A ion concentration has increased, so A ions are going to react with B ions to precipitate AB, decreasing solubility. So when we say common ion effect, by definition, it refers to the precipitation what do we precipitate? Of a sparingly soluble ionic salt. Precipitation of a sparingly soluble compound or ionic salt, sparingly soluble ionic salt from where? From its saturated solution, when a more soluble ionic salt when a more soluble ionic salt, when a more soluble ionic salt with a common ion, is added to the saturated solution, at a given temperature. Precipitation, because you can see by adding a more soluble solute SC, which has got a common ion, we precipitated a sparingly soluble solute we had. So it is the precipitation of a sparingly soluble ionic solute from its saturated solution when a more soluble ionic solute with a common ion is added to the saturated solution at a given temperature. As simple as that. As simple as that. As simple as that. All right. So now, after having known the definition, I can give you a live example now using common compounds, a live example of common ion effect. For example, if you add a solution, of lead to nitrate, if we add a solution of lead to nitrate, because you know all nitrates are soluble, if you add a solution of lead to nitrate to a sparingly soluble solution or to a saturated solution, to a saturated solution of lead to chloride. Wow. Lead to chloride is a saturated solution. We are adding a more soluble lead to nitrate. This one precipitates a saturated solution, which is lead to chloride, precipitates lead to chloride. Because I can denote my because with a reason, or rather with equation. Initially, you had lead to chloride to form Pb ions plus 2Cl minus. Addition of lead to nitrate increases the solubility. Addition of lead to nitrate increases the concentration of lead to ions, because lead to nitrate solution being soluble, it will ionize to form lead to ions and nitrate ions. Now, the lead 2 ions formed from lead 2 nitrate are said to be common ion to lead 2 ions in the saturated solution of lead 2 chloride. Okay, so to restore the equilibrium, the chloride ions have to react with a common ion lead, okay, to precipitate lead 2 chloride, which shifts the equilibrium from right to left. And as the equilibrium shifts from right to left, there is a decrease in solubility. So this is a live example of common ion effect. Another example, look at silver chloride. You have sparingly, or you have a saturated solution of silver chloride, but adding like silver nitrate. Adding silver nitrate. This is sparingly soluble, so it dissolves in water and establishes equilibrium between silver ions and chloride ions. But addition of silver nitrate increases the concentration of silver ions in that the silver nitrate will ionize, produce silver ions and nitrate ions. So to maintain the equilibrium, the silver nitrate from the common ion will react with the chloride ions, and the equilibrium will shift from right to left. Why does it shift from right to left? Because you are precipitating what you had at the left-hand side. This is the left-hand side, this is the right-hand side. When the equilibrium goes back to give you the initial reactants, then it means that it has shifted from right to left. As it does so, there is a decrease in solubility. So all logic behind that is what we call common ion effect. Common ion effect. Now, I'm going to write maybe what one would do, talk about for this case, addition, the effect of adding lead to nitrate. We say that it decreases solubility, but let me summarize for you how. You say that a lead 2 chloride initially dissolves in water to establish equilibrium between lead 2 ions and chloride ions, okay? Addition of lead 2 nitrate to the above equilibrium or to this equilibrium will increase the concentration of lead 2 ions in solution. You write the equation. Now, the lead 2 ions from lead 2 nitrate are said to be common ion to the lead 2 ions in a saturated solution of lead 2 chloride. So to restore the equilibrium, the chloride ions react with excess lead 2 ions to precipitate lead 2 chloride, shifting the equilibrium from right to left. This reduces the solubility of lead 2 chloride. We are going to look at calculations. Calculations are going to demystify the aspect of whatever we are talking about. Okay, so let's look at this example, calculations. Calculations. Number 1. The solubility product of aluminum hydroxide is 1 times 10 to the power negative 33 moles power 4 decimeter power negative 12. Calculate the Roman 1 solubility of aluminum hydroxide in water in moles per decimeter cubed. Roman 2 solubility of aluminum hydroxide in 0.01 molar sodium hydroxide solution. Roman 3 mass of aluminum hydroxide precipitated precipitated after addition of 0.01 molar sodium hydroxide. That's the question that we are having. This is the challenge ahead of us. Now, for Roman 1, they have told us that the solubility product, we have been given the solubility product. Now, if you're given the solubility product of aluminium hydroxide, of course, we need to first obtain the expression for KSP. How do we get the expression for KSP? How do we get the expression for KSP? Now, to get the expression for KSP first, we need to first write the equation. I want to first teach you the skill of answering this question. They have not asked the equation, they have not asked the expression, but those are the guides to take you through. Number 2, they have first asked you the solubility of aluminium hydroxide in water. In water. This one you calculate it normally, that we have been calculating solubilities. But when they say solubility of aluminium hydroxide in sodium hydroxide, you had aluminium hydroxide, now they are adding sodium hydroxide. It implies that there is an introduction of a common ion. You had aluminium hydroxide, you have sodium hydroxide, meaning the hydroxide ion is common in each. So I expect the value of solubility that you're going to get on Roman 2 to be less than the one in Roman 1. So the solubility in water will always be greater than the solubility in presence of a common ion. The moment you know that, then it becomes very, very, very easy for you to push on. So we shall have aluminium hydroxide first. Aluminium hydroxide solid plus aqueous shall form aluminium ion and hydroxide ions, 3 of them. Now, implying that the KSP here, the KSP value is the concentration of aluminium times the concentration of hydroxide ion to the power 3. To the power 3. Now, they want the solubility of sodium hydroxide. I don't know it. Let the solubility of aluminium hydroxide in water be X moles per decimeter cubed. So if for aluminium hydroxide is X, then now it means that the concentration, individual concentration of aluminium ions will be X moles per decimeter cubed, while the concentration of hydroxide ions, by looking at the molar ratio, it's 1 to 3, so it will be 3X moles per decimeter cubed. Implying that by substituting in the formula of KSP, it would be, KSP was given as 1 exponent negative 33, is going to be equaling to the concentration of aluminium, which is X, times concentration of hydroxide, 3X then cubed. I told you that a lot of care should be put on this. So 1 exponent negative 33 is equal to 3 cubed, that is 27, X cubed then times X, that is 27 X to the power 4. Implying that X to the power 4 alone would be 1 exponent negative 33 out of 27. So if you need X, you'll take the fourth root. You take the fourth root of 1 exponent negative 33 out of 27. So X, after computing this fourth root, let me see. It is going to be 2.467 times 10 to the power negative 9. And therefore, you conclude that the solubility of aluminum hydroxide in water is this moles per decimeter cubed. You note this value. You have to note this value because now we are going for part 2, where they want us to get the solubility of aluminum hydroxide in 0.01 molar sodium hydroxide. Now, that is where we have to be too much focused as we move on. They have given us, for Roman 2, they have introduced 0.01 molar sodium hydroxide. Remember, we had our KSP is given the value, the solubility product, 1 exponent negative 33, it does not change, moles power 4, decimeter to the power negative 12, okay? Still, we know that KSP is equals to the concentration of aluminum ion times the concentration of hydroxide ion raised to the power 3. Now, here, we shall also let solubility, because now we are getting solubility in a different substance, solubility of aluminum hydroxide in sodium hydroxide, let me let it to be Y. So if it is to be Y, we have an assumption, because sometimes they ask you these assumptions. We assume that the concentration of hydroxide ion, that common ion, okay? We assume that its concentration in the final solution, okay, comes from the introduced substance. So it comes mainly sodium hydroxide, and the contribution from aluminum hydroxide is neglected. And the contribution from aluminum hydroxide is neglected. What do I mean? We are given a common ion. We are given a substance that has a common ion hydroxide. So we assume that the concentration of hydroxide ions in the final solution is from sodium hydroxide. And therefore, the concentration of hydroxide ion in aluminum hydroxide is neglected, implying that the concentration of OH in this particular case will be 0.01 molar, because we have assumed that it comes from the introduced substance. Then for the case of aluminum, it is just Y. Regardless of the molar ratio or what not. This one is Y because we have, okay, it is 1 here. Okay, it is during the, and in the equation, it is appearing as 1 aluminum ion. Okay, 1 mole of aluminum ion. Therefore, it is Y. But for the hydroxide, we say that it mainly comes from the solution introduced, implying that by substituting in KSP expression, it will be 1 exponent negative 33, KSP does not change being a constant, is equal to the concentration of aluminum. The concentration of aluminum ion, we say that it is Y, times the concentration of hydroxide, which is 0.01, then cubed. Okay, so Y would mean that it will be 1 exponent negative 33 out of 0.01, then cubed. This one will give you the value of Y. This one will give you the value of Y as, to give you the value of Y as 1 times 10 to the power negative 27. Implying that the solubility, because you had let it to be Y, so the solubility of aluminium hydroxide in sodium hydroxide is 1 exponent negative 27 moles per decimeter cubed. Then here we can say moles per decimeter cubed. Now, after getting this solubility now, we have got solubility in water and solubility in sodium hydroxide, or the common iron, the solubility in the common iron. Now, the final part wants us to find the mass. The final part wants us to find the mass of aluminium hydroxide precipitated after adding sodium hydroxide. So, to get mass of sodium hydroxide precipitated, rather to get mass of aluminium hydroxide precipitated, we need to first get moles precipitated. Moles of aluminium hydroxide precipitated are going to be equal to the initial solubility in water, the concentration in water, which was 2.467 exponent negative 9 minus the one in sodium hydroxide, which is 1 exponent negative 27. And this one gives us the moles precipitated as 2.467 exponent negative 9. But it does not mean that they must be the same. But by coincidence, it is the same. Moles per decimeter cubed. Now, in other words, when we want moles precipitated, we subtract the solubility in water minus the solubility in the solution containing a common iron. Then now, these are moles precipitated. So can we get the mass precipitated? Of course, to get mass, you need to first get the molar mass of aluminium hydroxide. Aluminium is 27. Aluminium is 27 plus 16 times 3, then plus 1 times 3. And this one gives us 78 grams, meaning that 1 mole weighs 78 grams because molar mass means the mass of a substance in 1 mole. So 1 mole of aluminium hydroxide weighs 78 grams. What about these moles? 2.467 exponent negative 9 moles weigh 78 times 2.467 exponent negative 9 grams. So on multiplying, you're going to get 1.924 exponent negative 7 grams per decimeter cubed. So that is the mass precipitated. So the mass precipitated is 1.924 exponent negative 7 grams per decimeter cubed. All right. All right, all right, all right, all right, all right. That is what we are having. That is what we are having. So let me do you example 2 about this. Let me do you example 2. Example 2. The solubility product of calcium iodate is 1.69 exponent negative 9 moles cubed per liter negative 3. at 25 degrees Celsius. Roman 1 is calculate the concentration of iodate ions in a saturated solution, of calcium iodate at 25 degrees Celsius, and Roman 2, 0.1 molar calcium nitrate was added to a saturated solution of calcium iodate and the mixture stirred. Capture the mass of calcium iodate which was precipitated. Calculate the mass of calcium iodate which was precipitated the mass of calcium iodate which was precipitated. State assumptions made. That is the question. So actually this question should bring out the clear understanding of what we are discussing, okay? They've given us the solubility product, KSP, of calcium iodate. So they want us to get the concentration of iodate ions. They want us to get the concentration of iodate ions. Now, for that Roman 1, we need to first write the equation for solubility of calcium iodate. Plus aqueous form calcium ions plus 2 iodate ions. After writing the equation for solubility, then we can come up with KSP expression. KSP, concentration of calcium, times the concentration of iodate ions. Okay, so, well, they want the concentration of iodate ions, but we can get it by letting the solubility of calcium iodate be, since it is moles per liter, we can let it to be X moles per liter, implying that the concentration of calcium, if the concentration of calcium is X moles per liter, then the concentration of iodate, actually here it is power 2 because of the ratio squared. So iodate ions will be twice X moles per liter, implying that when we plug the information given of KSP into this expression, we are going to get 1.69 times 10 to the power -9 is equal to concentration of calcium, which is X, times concentration of iodate, which is 2X squared. So 1.69 exponent negative 9 is 4X cubed. Implying that the value of X would be equaling to the cube root of 1.69 exponent negative 9, we divide it by 4. So here we shall get the value of X as 7.5 exponent negative 4. Remember, we had said that the concentration of iodate is 2X, but the concentration of iodate ion is 2X. So it will be 2 times 7.5 exponent negative 4. So this one will give us 1.5 times 10 to the power negative 3 moles per liter. So that is the concentration of iodate ions as required. Okay, but the solubility, remember, though they needed the concentration of iodate ions, but the solubility would be X, which is this. So if they wanted us to get the solubility in water, it would be this. Part 2, they have added 0.1 molar calcium nitrate. But remember, you had calcium iodate. Interesting. This is very, very, very interesting. Now, they have added 0.1 molar calcium nitrate. What does it mean? It means that here, and you had, remember, you had calcium iodate. So since we had iodate and we've added a nitrate, it means that we have introduced, of course, iodate, you have to put it outside. It means that we've introduced calcium as our common ion, okay? Okay, so I'm going to have my concentration of calcium ion. In this case, we shall state the assumptions. Concentration of calcium ion would be the same as 0.1 moles per liter. Why? Because we said that we assume that the concentration of the ion, which is common, is gotten from the substance introduced, which is the calcium nitrate. So the contribution of the concentration of calcium in calcium iodate is neglected. So the concentration of calcium ion, the common ion, is 0.1. Then maybe we can say that the concentration of iodate we can let it to be maybe Y moles per liter. So that from KSP is equals to concentration of calcium ion times concentration of iodate ion squared. It would mean that 1.69 exponent negative 9 would be 0.1 times Y squared. So here we can get the value of Y. It means that Y squared is equals to 1.69 exponent negative 9 over 0.1. So we can get Y as the square root of 1.69 exponent negative 9 or 0.1. So your Y is the square root of that, which is 1.3 exponent negative 4. So the concentration of iodate ions is equals to Y, which is equals to 1.3 times 10 to the power negative 4 moles per liter. Meaning that if we need the concentration of calcium iodate and therefore the solubility is going to be equaling to, because by molar ratio, it will be divided by 2. If the iodate is 2, if in the equation we have 2 on iodate, So it means that for calcium iodate, it will be just a half of that. So it is 1.3 times 10 to the power -4. We divide it by 2. So the concentration of calcium iodate is 6.5 times 10 to the power -5 moles per liter. But remember, this is the concentration of calcium iodate or the solubility of calcium iodate in presence of calcium nitrate. But initially, in presence of water, you add the concentration or you add the solubility in presence of water as 7.5 exponent -4. So the calcium iodate concentration in water was equal to 7.5, it was the value of x, 7.5 exponent -4. So here we can get moles precipitated. Moles of calcium iodate precipitated would be 7.5, the one in water, exponent -4. We subtract 6.5 exponent -5. And this will give us 6.853 times 10 to the power -4 moles. These are the moles precipitated. After getting moles precipitated, you can get mass precipitated by getting the molar mass. The molar mass of calcium iodate is 390 grams. Calcium is 40. You substitute for each atomic mass, okay? And then we calculate because for iodine is 127, so you have calcium 40 plus iodine 127 times 2, because there are 2 atoms of iodine, then plus 16 times 6. So it will give you 390. It means that 390 grams are for 1 mole. So you will say 1 mole of calcium iodate weighs 390 grams. What about 6.853 exponent -4 moles? They will weigh 390 times 6.853 times 10 to the power -4. So this one will give us the mass precipitated as 0.267 grams. That is the mass precipitated. That is the mass precipitated. Mass precipitated. 0.267. Assumptions made. Assumptions made is that there is no change in temperature. No change in temperature occurs. 2 is that the concentration of calcium ion is the same as 0.1 molar, implying that I can say i.e. the concentration of calcium ion from dissolved calcium iodate is ignored. Then another thing is that there is no change in the total volume of the solution. No change in the total volume of the solution. No change in the total volume of the solution. No change in the total volume of the solution. Okay. Allow me do my final question. Allow me do my final question. Then I'll give you one question to do on your own. And you see. Let me do one more question, then I give you one question to do on your own. Let me make it shorter. The solubility product of silver ethane dioate is 5.3 times 10 to the power -2 moles cubed, liter power -3 at 25 degrees Celsius. Calculate the concentration of one, this is, let me call it part A, of 1 silver ions and 2 ethane dioate ions. Part B, calculate the mass of silver nitrate that should be added. Calculate the mass of silver nitrate that should be added to the saturated solution in B, okay, in A, to reduce the concentration of ethane dioate ions to a fifth of its original value. After this question, I would expect you to do every question that involves common ion effect. Well, for part A, if they want us to get the solubility, rather the concentration of these independent ions, then we need to first select the solubility of silver ethane dioate be maybe X. If the solubility of ethane dioate and of silver ethane dioate be X, and you know that this one here so it would mean that the KSP would be equaling to concentration of silver ion raised to the power 2 times the concentration of oxalate or ethane dioate ions raised to the power 1. But if the solubility is X, then the concentration of silver ion will be, by the mole ratio, it will be 2X, while the concentration of the oxalate ion would be X, implying that like a SP value, which is given as 5.3 exponent negative 2 is equal to silver squared. So it is 2x, then squared, then times x for oxalate. So 5.3 exponent negative 2 is 4x cubed. Implying that the value of x is the same as the cube root, since we have x cubed, so it should be the cube root of 5.3 exponent negative 2 out of 4. So we shall have x as 0.2366. Since you've said that the concentration of silver is 2x, concentration of silver ion is 2x, so it will be 2 times 0.2366, and this will be 0.4732 molar or moles per liter. Then the concentration of oxalate ion or ethane dioate ion, we say that it is X, and we've gotten the value of X as 0.2366 molar. Part A is done. Part A is done. Then now they are saying, calculate the mass of silver nitrate. Remember you had silver ethane dioate, which is sparingly soluble. Now they want us to calculate the mass of silver nitrate, which is soluble, that should be added. See a common ion? So they want the mass of silver nitrate that should be added. Okay? So that we reduce the concentration of ethane dioate to a fifth of original value. Now, it means that for part B, we shall put into consideration of the following. We shall look for the new concentration. We shall look for the new concentration of ethane dioate ions. New concentration of ethane dioate ions. It will be a fifth of the original ethane dioate ion, original 0.2366. So the fifth of that is going to be 0.0473. Now, the new oxalate concentration is this. It implies that our new KSP value is going to be equal to the concentration of silver squared. So we shall have the concentration of silver squared times the concentration of oxalate times the concentration of oxalate ion. So substitute KSP is 5.3 exponent negative 2 is equal to silver ion. We don't know it. But oxalate, we have gotten it, 0.0473. So first get the silver ion concentration. Silver ion concentration will be 5.3 times 10 to the power negative 2 over 0.0473 under the square root. So the silver ion concentration is going to be equal to, when you take the root of this, 1.058 molar. Now, to get moles of silver ion required, because if they say calculate the mass of silver nitrate, you see the common ion is silver, silver ethane dioate, silver nitrate. So we need the mass of silver nitrate. So we need here the moles of a common ion required. So moles of silver ion required would be equaling to 1.058 minus the concentration of silver initially, which is 0.4732. So the moles of silver required are 0.5 0.848. But the concentration of silver, by the assumption of a common ion, being a common ion, its concentration is originally is the same as the concentration of the added substance. So the moment I get moles of silver ion, then I've gotten moles of silver nitrate, because we've said that silver ion is assumed to come from the added substance. Then the moles of the sparing insoluble substance is neglected. So we neglect silver nitrate and we assume the moles of silver ions to be the same as the moles of silver nitrate. So after having gotten moles of silver ion required, now I can get the mass of silver nitrate. Okay, so I have moles as those ones. I'm going to move with them. So moles of silver nitrate are 0.5848. These are the moles required. So I can get relative formula mass of silver nitrate. Silver is 108, nitrogen is 14, while oxygen is 16 times 3. This is 108 plus 14 plus 48, which gives us 170. Now, it means that 1 mole of silver nitrate weighs 170 grams. What about 0.5848 moles of silver nitrate will weigh 170 times 0.5848 grams. And this one will give us the mass weighed as 99.416 grams. So this is the mass of silver nitrate that should be added to reduce the concentration of ethane dioxide to a fifth of the original concentration. I'm going to give you one number to try, then other numbers. Maybe as we progress, they will be coming on board. A saturated solution of silver oxalate contains of silver oxalate contains 1.1 times 10 to the power -4 moles of silver oxalate per liter at 25 degrees Celsius. Calculate the solubility product of silver oxalate at 25 degrees Celsius and indicate its units. Three and a half marks. Now, to approach this question, you have to have understood the work in the second video, because now they have given you solubility, they want KSP. So you have to be technically smart. You have to be technically smart. Then B, determine the solubility of silver oxalate in a 0.01 molar silver nitrate solution. State any assumptions made. For max. For max. And then, yeah, for that particular case, those questions, that question can guide you through. It can guide you through. Maybe can do also this, can do this. The solubility product of calcium sulfate at 25 degrees Celsius is 2.4 times 10 power negative 5 mole square decimeter power negative 6. Calculate the solubility of calcium sulfate in moles per decimeter cubed in A, water, B, 0.5 molar sulfuric acid. Let me call this one Roman 1, Roman 2. Then I call this one part A. Then part B, state one condition under which solubility product is valid. Condition under which solubility product is valid. So by doing this, you will be safe to go. I wish you all the best till we meet next time.